Okay, so welcome everyone. This is not a formal lecture today, but just to get to know each other a little bit. So my name is Min. I'm a lecturer here in SOC, and I normally do natural language processing. But because I've run this section of 6101 last semester, we did NLP, deep learning for NLP. I thought it would be fun to do something else so that I can learn. And then you can learn as well. So you may already know we're following the Stanford lectures done by Prof. Lee and two of her PhD students. So they've put up this very nice site, which I'm sure you've looked at by now, which is Convolutional Neural Networks for Visual Recognition. And they have a lot of nice demos. So I encourage you to go through this. In fact, you'll have to if you're an NUS PhD student. Which ones of you are first-year PhD students who are allocated to the course? Okay, pretty much everyone. Great. Okay, so you all are going to disappear in about 20 minutes, right? Okay, so I'll just go over the basics here. So as of week 3, when we start the actual course, we're going to have members of the public come down. We expect to get pretty full house, so this entire classroom should be pretty full. But we cannot teach in such classes because, of course, you have to pay school fees to the school if you're a PhD student. That's given by the central government. But for community people to come in, we can't teach. So basically what we're organizing is a study group. Okay, so we're going to work like a study group. We're all going to give lectures to each other, and we're going to ask questions to each other, and that's how it's going to work. Okay, so when you've ever studied a course online or things like this is what happens. You know, 95% of people who start courses don't finish them, right? They just enroll and say, oh, I'd like to do some deep learning, and then after the semester gets busy, they drop. Okay, so in order to try to mitigate that to some extent, what we want to do is to ensure that you have enough participation. And there is a lot of factual knowledge about how people learn. They learn best when they're engaged. Okay, so it's not about lecturing, it's about participating. And that's what a study group is for. I mean, all of the YouTube videos from Fei Lee are already online. You can watch them. They'll be better than what each of us can do. Right, but that's not the point. The point is to present so that you can learn, right? And to present and ask questions so you can learn, not to outdo, you know, what those students and professors are doing, but to complement it for our own purposes. Okay, so that means that every one of you in class will have to do 2 things, right? You'll have to do a presentation, okay, meaning that you'll have to do one of the actual lectures that are on YouTube. You have to watch it, you have to review the material, and then use the slides and present against the slides. Okay, and you will also have to be a questioner, meaning for an additional week, you will have to prepare questions for discussion. Okay, now the YouTube lectures are only about an hour long. Okay, so ostensibly each week we only have to give a lecture for an hour, but that's why we have questioner roles, okay? Because typically we want to ask questions about the material, and as a class, not as the lecturer for that presentation, figure out the answer, okay? So of course, Fei and Justin and Serena know the answer to most of the questions, but of course you don't. You're students for the most part. You may have done some machine learning or deep neural networks on your own, but that doesn't mean you necessarily know. Okay, so for that reason, we're going to work as a group together to try to understand the material. Okay, so later on, I'm going to share a link where you will need to actually put your names down in a spreadsheet about which weeks in the schedule you want to present and you want to ask questions, okay? And that'll be from week 3 onwards, right? So week 3 to week 7 for, sorry, week 3 to recess week for the first set of people, and week 7 to 13 for the rest of them, okay? So I don't know if you've seen this. Has everyone seen the playlist from Stanford? Yeah. Okay, so this is their lecture collection for their things. So they actually have already done the slides. Okay, they've actually given the lectures. So actually your work as a presenter is just to repeat what they've already said. Okay, but by doing that, you also feel a bit more confident presenting the material. And many of you may not be first language speakers of English, and it will help you overcome your fear of speaking. I mean, you are in a group of friends, so to speak, because we're all here as students, okay? There's no shame in doing it incorrectly or wrong. I mean, that's why we do it as a lecture group, as a study group, okay? So whoever's standing up here, you give them some slack, right? Not the Slack software, but cut them some slack, meaning that, you know, if you get it wrong, it's okay. I mean, we're doing this together, okay? So you can use the short link that I just showed you, right, that I created last night, or you can just find it through YouTube, go to the playlist, listen to the lectures that you're going to present, and you can listen to the lecture before you come to class when you're I mean, as study material, so when a person represents it in class, you'll be able to understand it better. Okay? I think that's good study habits. Okay? So aside from this, those of you who are coming in from industry, anyone here from industry today? Only one? Okay, one today. Okay, thanks for coming. So we will ask you to also follow through and do a project based on the course. Okay, so the Stanford students actually have to do a project, right? You probably know that. They actually have 3 homework assignments in one big project where they do group work to come up with a vision project on their own. So I encourage everyone in the class to do it. It'll certainly further your understanding, but of course, many of you are very busy, okay? So I won't obligate that, okay? But I think, especially for industry participants, if you actually want to get something out of coming all the way to NUS for 2 hours every week, then you should really put in some effort. Animesh, did you have a question? No, just stretching, okay. So what we'll do is we'll try to organize a poster session for all of the people who come in for the class in industry to participate on this, okay? So I expect much more people in week 3 because that's actually the formal start of the course. So many people are covering the first 3 lectures on their own. Okay, so you already know yesterday night I asked you guys in Slack to put in your choice of day, and obviously Thursday is not a good choice because it conflicts with the other deep learning course. So that's fine. You guys will move it to another day. So we'll choose another day through the Slack poll when you guys are available. Okay, and there'll be different days potentially for the first and second half, right? Because there are different students in the lab rotation. And the first half will choose their best day, and the second half will choose their best day, and we'll have to deal with that. People from industry will just have to deal with that. You know, if you can attend both halves of the session, that's great. Okay. Okay. So my field of research is not vision, as I said earlier. My field is natural language processing and digital libraries, and I'm just having some fun organizing this study group because I also want to know what's going on in vision. Okay, and you know, well, lecturers can also learn what's going on. Okay, so I already told you about this, so I'm not going to cover that. And I'd like you to also spend some time keeping the Slack conversation alive. And last year, we had a number of people actually come on Slack and participate quite often. And I think that's a very good thing to do because it encourages more conversation during the day. Okay, so that's what we're going to use right now. Until we get big enough that Slack doesn't work for us, we're not going to open up other social media channels for the course. Okay, any questions so far? No? Okay. I think that was it. So To do the projects and the assignments, there's no assignments for our course, but the Stanford people have assignments. If you want to do their assignments, you're certainly welcome to. You probably need access to compute resources. So unfortunately, we don't have that. Stanford has such resources, but can try. Yeah. So if you know how to access that or apply for that, everyone with okay. So maybe it's all in. You can put a post on Slack and tell people how to use that. I don't think everyone knows. Does everyone know how to use the NSCC computer? So there's a national supercomputing cluster that has some GPUs, machines. I think. Yeah, but they're K80s, I think. K80s or K40s, right? They're pretty old. Yeah. So there's some. They're not particularly new GPUs. You can use those. Yeah. No, they won't do that, but yeah. It's a bit troublesome. Yeah. Are you going to the design class? Yeah. He has instructions on how to do that. Yeah. With TensorFlow. How to use NSCC. Yeah, so if you guys are all going to migrate over to that class, then that might be a good thing to put into the Slack group if there are instructions, so that outside participants who have access to NSCC as well can use that, right? Because yeah, they're pretty much bare metal cluster, right? And there's not much things on there. 24 hours. That's not too bad. You can run some reasonable size sets of data through that. And the queue is a bit long. Sometimes you wait about 4 or 5 hours. Okay, yeah, so it's not for deadline-oriented things, but for classwork, it's okay. Right. Yeah, okay. So that's what I wanted to cover with you. I wanted to go to Slack for a minute. How come it's not showing up? And I wanted to give you the URL for the spreadsheet. And I'll post it into Slack as well. But it's actually there. It's the same spreadsheet that we used last year for the course. And what I'd like you to do between now and week 3 is, you know, talk with your friends in the course, or if you don't know anyone, make friends in the course, right? And then find out which session do you want to do. So I'm gonna go find it. It's quite a bit back. So this was our final paratha dinner last semester. Shallow breads for deep learning. Okay. Okay, here we go. I need to change the title, but never mind. Okay, so what you're going to do is basically follow this template, all right? What I'd like you to do is fill in your name, you know, as in your matrix number or whatever, okay? Tell us where you're from. So if you're from NUS, NOC, SOC, just write that. Okay. You already are knowing whether you're enrolled in session 1 or session 2. Session 1 is for the first half of the semester. Session 2 is for the second half. You could enroll for both if you're interested in from industry, or neither if you just want to watch online. Okay, so I'm going to be here for all the sessions. Okay, and then you have to specify which 2 weeks you want to do. Okay, so the first column, this D column, is for the presenter role. Okay, and this one is for the questioner role. Okay, so how does that work? Well, you just go back to the course homepage, you scroll down here, and you pick something that you want to do. So for example, you want to do week 3, you want to introduce neural networks to the class, or you want to go through convolutional neural networks, or maybe you're interested in actually going through the CNN architectures that people did. If you're from the first half of class, then you would write that here. So let's say I want to do week 7, then I'll say, pick week 7. Okay, and for the questioner role, again, you're just picking one other class that you're interested in, but you could be a questioner instead. So for example, I don't know much about how to use Python, so maybe I want to learn about Keras, but I'm not confident presenting it, so I could ask about this. So this would be recess week, and I could put something like recess week. Okay, and we have this homepage. If you'd like your name on the homepage, you can just fill in a web address here that you want listed. That's mostly for, well, anyone, especially external folks who want to say that they've taken the course. Okay, so you need to do this within the next 3 weeks or so. Okay, just do this, and then we will be able to allocate you 2 weeks. Okay, within Slack. Okay, hope that does work. Okay, you'll see that there's some channels here. Sorry. Okay, so oh, that's not good. You have channels for each of the weeks. Okay, so if you decide and you get allocated, let's say to week 7, okay, what I'll ask you to do is join that particular week's channel, okay, and then you will coordinate with the other people who are selected for that week, and then you can divvy up the work. Right, so for example, if there are 20 slides and 2 presenters, then somebody take the first 10, somebody take the second 10, and then you trade off to present. If you're in the questioner role, then you can also work with the presenters to say who's going to ask what questions and things like that. Okay, it's to generate discussion. Presenters, just are responsible for the material here. Questioners, in some ways, it would be good if you can go beyond what's in the slides. So for example, if you look at a topic and you search on archive, you find some interesting papers, then you can, upload that paper into the Slack, the general channel, and say, oh, I thought this was an interesting paper to discuss. Okay, and then we can talk about it then. Okay, so that is what I have for you. For those of you in the SOC PhD student group, just before you have to leave, these are the poll results so far. So it looks like it's either Monday 6 to 8, Monday 8 to 10, or Friday 8 to 10 right now. Okay, and I think we're going to choose Monday, but it depends. We still have a number of people who haven't taken the poll. So it's really important that everyone who selected this lab rotation can actually attend it. That's why I left the 8 to 10 slot out, because I think there's a good likelihood that you're not taking classes from 8 to 10 at night. Okay, so we will wait until everyone has participated on that, and then we'll assign the class accordingly. Okay, and for the second half, it looks like Tuesdays 8 to 10 looks like it works the best, but there are only 2 people who have polled for that out of 7, so that's likely to change. Okay. So that's it. So if you want to stay around for the actual lecture, that's fine. So the bulk of you who are going to the other paid deep learning class, that's fine. Yeah. Okay. Any questions? No? Okay. So that's all. So who's staying for the rest of the lectures? Okay, 1, 2, 3. Okay. So we're just going to go through the slides that they have. Okay, so why don't I first get you a second to talk about where you're from and your interests. Maybe we can all move to the front. Can we do that? Just like come to the first 2 rows here. And then you guys can tell me a little bit about yourself. Okay, let's start over here. Which do you want to start? Can you introduce yourself and tell us about where you come from and what type of interest you have in deep learning?
My name is Muthu. I'm a 4th year, hopefully final year PhD student with me in the web IR NLP group. I work on applying machine learning, NLP, and IR on education technology data. That's the research. I'm also interested in working on scientific document summarization, corpus, and chat tasks. For deep learning, I am anyway collaborating on various different projects which are implemented as a publication, but yeah, mostly we are working on scientific document data and forums.
Okay. Divish?
Hello, I'm Divish. So I'm an undergraduate student, 4th year, and I'm interning at Think Tank and working with Muthu and
Hi, I'm also 4th year PhD student. I'm working in the my interests are in using deep learning for different kinds of structure recovery from scientific documents, keyword, citation provenances, maybe some higher order structures which are specific to scientific documents. So I did it the last year at deep learning for NLP. So just trying to.
Sir?
Yeah, hi, I'm Jishnu. I just graduated from the undergrad program this last December, and I've been working as a software engineer at Google for like 6 months. I have like no particular application of interest for deep learning, just wanted to improve my understanding of the subject beyond like the level 4 classes that I took.
Okay, great. Thanks, Jishnu. Over here.
I'm Rizal. I'm currently working in the cybersecurity industry. I'm not from NUS.
Okay. Where are you from originally?
SMU.
SMU, great. Great to have you here.
I'm also just trying to explore more machine learning.
Which firm are you working with?
It's a small startup called Dinner Dynamics.
Dinner Dynamics?
Yeah, we actually sell different kind of cybersecurity products.
Okay. Thank you. Sir?
Oh, hi, I'm William. I'm still in NS. I'll be enrolling in NUS in 2019. So I learned about deep learning when I was an intern in like my JC research thing. So I'm just here to expand my knowledge more.
Okay.
Yeah.
You're probably the youngest member of our group so far. Yes?
Okay, I'm Roger. Undergrad, finally. I'm actually sort of skeptical, but I'm curious.
Okay. Yeah. Attending for fun. Yeah. Okay.
Kenneth, I'm not from here as well. I'm graduated from NUS, but I've been working as a doctor for 5 years. I'm thinking of learning deep learning to help in my applications and the startup that I'm trying to set up.
Okay, great. Welcome, Kenneth. Yes.
I am Jino Lee from South Korea. This is my first year of PhD study, so I'm looking for interesting research topics.
And Jinho, I think you're taking it as a formal course, right? You're one of the students who are enrolled, right?
Yes.
Okay. Great. So what we hope to do is build a community around deep learning centered here at NUS. So this is why we open this to the public, and especially those of you in industry, do make acquaintances with the people here, because these are good people who are also sharing your interests and potentially could work on projects with you. And as I alluded to at the earlier part of the lecture, we want all of the people in industry to actually do a project, right? So you know, you can meet with the students and especially people in my group, they're quite burdened, but I think these people have more long-term interest in deep learning outside of just doing a lab rotation, and they may be able to at least give you some advice about what to do. So with that, I'm just going to cover what I heard from Fei Li last night, because I watched her lectures. And as I said, you should do this yourself when you are preparing for the class, because there is this basically long YouTube list. So I'm going to go through, let's say, the first and the second lecture, and then the third lecture, if we have time, we can do, depending on how comfortable we all are with the math. Okay, if you guys are uncomfortable, we're going to slow down, because I think it's more important that everyone's on the same page rather than accelerating, because this is just prerequisite material. Okay. So again, even though it's a lecture, I mean, there's only like 10 of us here, so why don't we have more of a discussion? So if you've watched the materials and I've left out things, please say so. Okay, so this is the Convolutional Neural Network course at Stanford, and you can see there's so many different applications where we use sensors, especially optical ones, in many different settings, right? You have drones, you have camera phones, which is probably the most used sensor device on a phone now, even though you have other things like the accelerometer and the fingerprint sensor. And we all buy our phones, not so much just to talk to each other, but many times for the photo quality and for how well it takes pictures, and what other things you can enhance with that. So really, if you think about computer vision, it's one area, but it's really related to so many constellations of other fields that are out there. So for example, going back to the origins of, doesn't work anymore. Okay, going back to the origins of how vision started in biological creatures, we have to think about optics, right? And knowing how the brain processes will take on all of these other aspects in biology and psychology about how the brain is able to compute and understand edges and build up composite shapes. Okay, but there's also engineering aspects, right? Like if you're going to take a vision and put it into a tangible device, perhaps a robot. And there's also this entire quadrant that we are concerned with here, which is the math and science part, where we have to compute or create an algorithm that can take the visual output from a sensing device, right? That's just going to generate pixel values, right? And then be able to process that into some semantic representation, right? And that's a big problem because there's this semantic gap that people always talk about, which is basically that you have raw sensor data, like the level of amplitude from a microphone or RGB values coming out of a camera. What you see is something different than just RGB values, right? So we want to take that and those images and then recognize something and then use that for other types of work. Okay, so that's just to say that really vision is part of many, many different fields, and it's just gotten a life of its own after being a part of many different subfields in other areas for many years. Okay, so I'm not going to go over this, but basically Stanford has a whole bunch of different courses that are all learning courses. The one that we did previously was the Stanford class by Chris Manning and Richard Socher here, which was in NLP. So they've also put up their lectures this semester. Okay, so what we're going to do right now is give you a brief history of computer vision first, okay, so that you have some understanding about where this came from as a background. Okay, so life has actually been on Earth for a very long time. We have 4 billion years of Earth lifetime, and only in the last 1% of the history of the Earth we had living organisms. And even for that 1%, which is quite a long time, it's like 4 million years or so, or much more than that, we have had life. but there was a big change in the way things worked out. You know, there were organisms that lived on the planet Earth, but they just ate food when it, you know, touched them, and they grew, but they couldn't seek out food on their own. They just had to like photosynthesize or whatever, okay, but they couldn't seek out prey. And about 540 million years ago, that started to change. Why? Because the most primitive optics and vision originated in biological creatures, right? And what happened then was that you could see, right? The organisms could see, and they could respond to their environment rather than passively sit around, okay? What did that mean? They became mobile. They were able to seek out their food, seek out their prey. And of course, if you had eyes and you saw something bigger coming your way, that means you probably wanted to run the other way, right, to avoid being eaten. So that impact in biology about 543 million years ago caused a very big flourishing of different species to come about. Okay, and so before that, life wasn't very interesting because it was just passive. Now it became active because organisms were able to respond to their environment. So the basic versions of eyes are not very different from the first types of vision devices that we had engineered as humans, right? So even back to the Renaissance period, we had the camera Obscura, which was invented in several different guises, like Leonardo da Vinci's devices in the 16th century, which basically was what we call nowadays is the pinhole camera. A wall, you put a pinhole in it, and then the light comes through, and then you have an imaging surface, like you can see here on this side, where the plane is flat and just a surface that can project the light through. And of course, we know the optics of this. The image comes up upside down, right, and reversed, and then we have to do some internal computation biologically to flip that upside up and right side around. Okay, so many devices were based on this primitive system of just having a keyhole and then having an image plastered on an imaging plane. And you can think about most of the ways that sensors are built now, the engineering sensors are still based on very similar optics, right? You have a lens that focuses to a certain optical depth, and then you image it on a sensor, a CCD or something like that, a charge coupled device, which allows you to record pixel values or brightness values. Okay, so around the 1950s, basically we started to study how organisms were able to understand what they saw. Okay, so one of the pioneer studies that Fei-Fei Li lectured about was this one, Huber and Wesso, in 1959, who studied advanced mammal, cats, and understood what they did by measuring what they did in their brain, by putting in, I think, electrodes. Okay, so basically, the idea was to, probe specific cells in their brain about what they were doing when they were shown images, right? And so what they could see was that certain parts of the brain had responds to certain types of visual responses, okay? So for example, you have cells in the cat's brains that can see edges, okay? Like up and down edges, or left to right, or diagonal edges, and that's all they do. They only activate when they see those types of vision artifacts. Okay, they can also see, particular spots, and more importantly, they sense movement. Right, movement was really important because of what we talked about earlier. You either had to run from your prey, or you had to chase your prey if you didn't want to die from starvation. Okay, so those were the simple cells, and we found out later on through this pioneering study that that was only part of the optic system, that there was indeed a hierarchy that was built up. Okay, and that hierarchy meant that there were other complex cells that took the output of those simple cells and built other more sophisticated primitives for that. Okay, so for example, you can say, oh, I saw an edge here, and then later on that edge has moved over here. So to do that requires some type of higher order computation, right? So you need an output of these simple cells to be able to do that. So these complex cells that are higher up in the hierarchy are basically doing that, responding to light and orientation and movement, right? But that's not all. I mean, if you have edges that move, you still don't know whether that edge is a prey or a predator, right? So you need to be able to distinguish that. So there are other complex cells on top of that that build on those primitives to realize structures, shapes, and organisms, right? And then help us and help other higher order mammals and other creatures realize, you know, whether it's food or something to run away from. Okay, and so right around that same time period in the 1960s, we had the first people in computer science, arguably at that time it was applied math, okay, who were starting to work on this problem. They're thinking about, okay, if we know all of these recent advances, I mean, 1960s, doing research on just, you know, same year type of research, they said, okay, now that we know that vision is a hierarchical structure in biological organisms, maybe we should be imitating biology. So we're going to start with vision as a set of primitives, right? So perhaps I'm given an image like in A, this is the original picture, and what I want to do is try to recognize what that is, and I'm going to take the same type of strategy. I'm going to build some algorithm to be able to find edges, okay, and then use those edges or this inventory of edges and then compose them into primitives like shapes, right? And from those shapes, then we could recognize a particular image as being a block of some style, okay? So they had to start with something simple, so they were geometric primitives, okay? So that was Robert's thesis in 1963, probably the first thesis on computer vision from that period. So that was pretty revolutionary. You look at that, this is only 4 years apart between the time that people first found out that vision was a hierarchical structure in biological organisms to the time when people were actually trying it out in an algorithm. Okay, so actually there was a project at MIT, which was just a summer intern project. Okay, so you know, this gentleman here said he's in JC. You know, he did some work, and we have some summer interns who are also here. They thought they could solve computer vision in a summer project, so they just got some spare student manpower around. This guy called Seymour Papert, you may know him. Does that name sound familiar to any one of you? He is the creator of Logo. Does anyone know Logo? It's a yes. It's a language for drawing pictures. Okay, you can ask the cursor to go forward and draw a line and then turn and then, you know, draw blocks or draw circles like this. This is an old language before MIT came up with Scratch and other things. Okay, so it was something that a lot of people were exposed to. So he was the pioneer of Logo much later on, but before that, he was a summer student, he was an intern, and he was working in the lab to do a summer project on solving computer vision. Okay, and as you know, decades later, after 1966, we still haven't solved the problem. We still have now tens of thousands of people working on computer vision, and it's very much an open and vibrant field. So it's quite funny. When you look at the early days of artificial intelligence, they said the same thing about natural language processing. You know, Alan Turing thought, you know, checkers would be much harder to solve than natural language processing. He was completely wrong about that, but never mind. Those are nice historical facts to know. Okay, another person that was very important was David Marr. Okay, he wrote one of the earlier theses on computer vision, and basically what he did was think about these representations of taking that early work from biology and converting it into an algorithm, right? So he said, okay, you have an input image, right? And you're going to just get some intensity values out. Okay, so you have RGB values, red, blue, and green values that you can put on a matrix or a raster plane. And then what are we going to do? We're going to think of a primal sketch as sort of like the simple cells in biology. Okay, so all I want to do is figure out these types of things. I want to know where things cross each other, where are big blobs of the same relative intensity and color, okay, whether there are lines that are straight or curved, and those will be the simple cells, the primal sketch, he said, of an image. So it's something like this gray image there. And then we're going to build a complex cell, like we saw in the earlier 1960 biological work, which is going to build slightly more big, larger primitives from that. So we're starting to recognize depth in a z coordinate, and to realize using some real-world a priori knowledge that certain things could be in front of each other. They could have some relation that's outside of the 2D frame that I'm receiving as from the pinhole camera. Okay, then we go on to a 3D model. The 3D model is basically the hypercomplex cell, right? Where we're taking that and really marrying it with our knowledge of the world and how things work, and understand the context of where that is, right? So we don't look at vision, a picture in isolation. For us, it's always like a movie, right? We don't get images in isolation. So we know that things are going to happen in a predictable way, and if they don't, well, we get excited. Our brains get alarmed when things suddenly happen, like trees are falling down and things like that. Okay, so all of these come about from this idea of taking the biological inspiration and trying to convert it into a computer algorithm that can recognize objects. So around that time, which is about 2 decades later, we start to have people think about this higher order structure, right? So you saw on this part the 3D model that's being presented. Back then it wasn't so fleshed out. The ideas that the primitives could be arrayed in different structure. There were 2 schools of thought here, which are basically somewhat equivalent, right? So you have the idea that you could build a primitive being just a cylinder, okay, that has a width, a diameter, and a length. And then you can say everything is composed of cylinders that way. Or you can think of, in this other one, the pictorial structure diagram, meaning that there are nodes of various sizes, spheres that are connected by edges of various length. Okay, so those were 2 different versions of the simple objects that were being created at that time to think about vision. Okay, so that was the start of what we were worrying about as a vision field, to think about object recognition, which is still a very standard problem that we need to solve in vision. Meaning, when I have an image, what do I see, right? What is there? Is it a person? Is it a car, etc.? But maybe that was a bit too hard to solve, because in fact, in reality, when you go back to these primitives, you can see even though we can recognize at the second level, simple objects that might be spheres or circles, it's very hard to recognize them as coins, because there's lots and lots of different types of problems here, right? These are all coins, but the edges are oriented differently. They could be slanted differently. And so to have a single algorithm that recognizes all of these as coins is not trivial in an exact form. So what people did was then think about around the late 1990s was, if object recognition is too hard, maybe we want to scale back and do sub-problems of that. Instead of recognizing entire objects, what we're going to do is segment them. All right, so this was work done at Berkeley, Shi and Malik in 1997, that introduced the normalized cuts algorithm to do what they call blob segmentation. Right, so the idea is that you can find patches of intensity of around the same importance and try to group them together, and then recognize these blobs as separate things, and then maybe write an algorithm or use machine learning to be able to draw all of these blobs together and say, okay, I see, a cluster of objects that could look like a shirt, a cluster of objects that could look like a face, and therefore I must have a person there. Okay. So one of the breakthroughs of computer vision was around 2000. Okay, when people from Microsoft, this is Viola and Jones, very famous, they created one of the first real-world applications to do face recognition. right? Now, of course, we know from biology that faces are very, very important things for people to recognize. You know, it's basically, we're innately wired to recognize faces and to understand when people are angry or sad or things of that sort, because it's important, again, from a survival perspective, to know whether someone's going to beat you up or is happy with you. Okay, so in fact, there had been a lot of studies before to try to recognize faces as primitive objects, and they mostly didn't succeed very well because the algorithms that they created, that we'll talk about later, were quite brittle. Okay, they didn't work very well when, let's say, you moved your face just a little bit off or the lighting was a little bit different. So coming up with algorithms that could do that turned out to be a very important thing. They published this paper in 2001, and Fujifilm was one of the first manufacturers to take this algorithm and put it into digital cameras very early on. Only 5 years later, after this algorithm came out, there were devices that could do this pretty much in real time. So you could take a picture that could recognize the face and try to do some image processing to sharpen up what the face looked like. Okay, like object recognition, as we said, was a very important problem, and we've already alluded to the fact that it's actually pretty difficult to do, right? Because there's we are imbued with a lot of real-world knowledge about how the physics and the real world looks, but a computer doesn't have access to that in general, right? So if we want to try to recognize an image and deal with objects that could be changed in many ways, we have to look for some primitives, some invariants, if you will. Okay, something that doesn't change when all of these conditions do. And one of the things that was coming out at the turn of the century was this idea of SIFT. Okay, it's basically a set of an algorithm that computes some set of key points that are within an object. Okay, so for example, this stop sign, you can see there's some specific dots that have been located by this algorithm, and these basically form a signature for the words STOP. All right, and so when I know just those pixel locations, if I can scale, transform, rotate, okay, those are simple operations to do on points. And if I see that in another image, I'm fairly reliably sure that I am seeing the same object. Okay, so this was one of the interesting techniques that came about that will be discussed later about being able to deal with an invariance in this fashion. But this was the first attempt to do this, not using the whole picture, because again, that's a lot of data, right? There's so many pixels that come out of an image. But here, to make this basically some type of hash or key to represent that entire image. So I only have to look at those specific points. I have to compute whether they exist in another photograph by looking at rotations of it and seeing whether it exists. Okay, so you can think of this as some type of summarization algorithm for an object, right? So usually you might think a stop sign has 8 sides, but here we're looking at the letters of the word to compute that that is actually a stop sign. Okay. So object recognition continued on. So in 2006 or so, there was more work to create scene understanding, to look at the entire image and say, what is going on? I mean, that is the holy grail of vision, is to say, when I look at an image, do I understand what it means? Okay, so for example, we'd say this is a landscape. What does it comprise of? And the idea behind this is to do something like the normalized cut algorithm that we saw earlier. Okay, which means that I take each part of the photograph and run a particular algorithm on that, and I look at the signature that's computed for that part of the algorithm, and I can know something about it, right? So at the top level, if I look at the whole image on the left, when I compute this algorithm, basically I get a signature that is quite general. Okay, but when I compute the specific quadrants, then I might get signatures that are more detailed, right? So for example, this pane over here, that's just sky, and if I just compute over that quadrant, it looks more like other sky quadrants that I've seen before. So I can get some understanding of what's going on in the scene, and then I can compose through an algorithm, say there's some sky at the top of this picture, there's some land at the bottom of the picture, so this must be a landscape of some sort. Okay, so to compute scene understanding by going at various resolutions, right? You can think of each of these quadrants again as being subdivided into 4 and running the algorithm again, and then being able to compose this. So this was a spatial type of pyramid approach to understanding what's going on in the scene. Okay, and this continued in several different other aspects. So histogram of gradients was basically an upgrade of the SIFT feature descriptors. We saw it on the stop sign one earlier. Basically, they were using wavelets to compute signatures of images to be able to detect what things are going on in the image. Okay, what's the orientation of the various important lines that were identified. And there were comparable algorithms developed in other groups to do this type of scene understanding, to compose various parts of the picture and put them together. Okay, so that was all the way until 2006, right? So 2006, at that time, we were still very much quite primitive. We couldn't do much in computer vision. And a lot of things changed in the past decade. I mean, really, things in vision have really taken off. And now we have systems that can see in some aspects as well as humans can. Okay, and why is that? There are a couple of reasons, okay? The first is that the community of vision as a whole decided that, okay, we are getting, you know, a lot of algorithms that are being computed, but it's very difficult to evaluate all of these algorithms because everyone has their own data set. They have their own images that they've trained on and tested, but there's no standard data set that everyone uses, okay? So the community came together and came up with this Pascal Visual Object Challenges, VOC, data set that many people contributed to. Basically, they found a lot of images on the internet, you know, on the web. They hired crowdsourced annotators to go and label all of these images and draw bounding boxes around them and assemble a data set that then many people could use. Okay, and starting with about 2006, you can see here, this is the accuracy or precision of how well systems performed. And then basically every year between 2006 to 2012, there was a steady linear increase in how well systems could do. Okay, starting all the way from back down here at about 15% to something pretty reasonable, making errors on maybe about 60% of the time it would get it wrong. But again, this was not just defining one single object, but 20 different types of objects. So they had person, train, airplane, but other things like cats and dogs and cars and things of this sort. So 20 object categories. Okay, well, with the VOC challenge, this data set that came out in 2006, all the way until 2012, they built on that, but they realized that, you know, this is really good. We're getting much farther because now we have more data and our computers are getting faster. Can we do more? Okay, yes, and actually Fei Fei, in part of her dissertation research and other work that was done as part of her vision group later, collaborated with people to make an even larger set. Okay, so they crowdsourced again many more images, and they said, well, you know, 20 categories is great, but the problem with 20 categories is it's really just 20. Why is that very important? One of the really important things about having just 20 categories is it means you can't recognize anything in the real world. Because, you know, even in the scene that you have now, you have hundreds of things that you know what you see, right? But if you think about it from a machine learning perspective, you have some background there, okay? What happens when you only have 20 object classes is that you are going to recognize everything as just those 20 classes, right? So things that are slightly human-like, you're going to say is human, right? And what that means is we're going to overfit the data, meaning that everything that you see is going to look like something that is one of those 20, and you can't recognize anything that you haven't seen before. So to get to the point where we can really do real scene understanding or understand the real world, we have to annotate many more types of things. Okay, so this was in collaboration with another project in natural language processing called Wordnet. So Wordnet is this hierarchical lexicon of words. Okay, and basically what they did is they took words in Wordnet, you can think about a dictionary, and then search for images on the web for that, okay, and then ask people to annotate all of those words. Like, is this I don't know, a computer? Is this a crowd? Is this a chair? Is this a handle? Okay, any word that you could find. They basically searched on the internet, the web, for those images, and then asked people through Amazon, Mechanical Turk, or crowdsourcing platforms whether it was that or not. Okay, and you can see some of the hierarchies that you got here. Like, as I said, Wordnet is basically a hierarchical structure. So you have things annotated as animals, for example, but animals are, of course, can be more specific than that. You can have birds, you can have fish, you can have mammals or invertebrates. So those were hierarchically classified, and the idea behind that was to try to put those together so that you could get some idea of some generalizability. Okay, so from the ImageNet database, they decided to create a shared task, something that everyone in the community could do, called the LSVRC, okay, which they basically subsampled the data set that they got from ImageNet, okay, 1,000 object classes, not so bad, okay, and 1 million images that they checked very reliably. Okay, so for example, if you had an algorithm that within the top 5 predictions, okay, of this picture was able to select the prominent thing that was there, it was considered correct. Okay, so even though there are other things here that might not be in the picture, if all 5 of these, the top 5 guesses were not in the picture, it would be considered wrong. Okay. This challenge happened over the last decade or so. You can see from 2010 up to now how well machines have done on that. Okay, and the very interesting thing about this graph here is that it's also a little bit linear, right? So here the graph is descending, meaning this is the error rate. So lower bars are obviously better, right? So what happened was about 2012, there was this big jump from 25.8% recognition rate to 16.4. Okay, that's a huge jump. It made the error reduction very significant, and teams didn't believe the output at first. They were like, how could that be? We expected maybe a couple percent different, but why more than 10%? Something must be, really, really powerful going on here. And that was the invention of AlexNet, which is one of the reasons why this course was being offered. Okay, so let's figure out why that is. Okay, so really, when you think about computer vision, there's so many different reasons that we look at it, because you can do object recognition, and object recognition is, in many cases, a composite problem. Like you can see here, there are people, even in NUS, who studied this problem about, you Instagram an image, can you figure out how many calories are there? So there's often the case that you have many different objects that you're eating, right? And then you want to first segment that image into those objects and then compute a calorie from a database, right? And you can think of other applications, like, for example, this one in the bottom left, which is, recognizing a painting, or on the bottom right, which is, augmented reality. So I have to do some scene understanding. I have to know the physics of what that place looks like, and then be able to drop a virtual piece of furniture in the right place that doesn't go through the floor, for example, or float in the air, right? Okay, so actually, computer vision, as we talked about in AlexNet and all the way up until this part here, where we can see that in 2015, actually computer systems can do as reliably as humans can do when faced with this problem. So what was this task? Like we said before, basically you're given an image and you have to decide what image out of what object is primarily in the picture out of 1,000 different things, okay? So if you can imagine doing this for hours at a time, okay, you would also fatigue in this, right? And it's hard for you to remember all of the 1,000 classes. This is why humans actually don't do that well at this task, right? We're sort of error prone because we don't remember all 1,000 things. We might choose something else, okay? But of course, computers don't have that problem. They don't have attention deficits, and we can train them to have attention to certain things instead. Okay, so we've alluded to object recognition, right? Object detection, but really we want to go for something much broader than that, right? So we want to do action classification, right? Because everything for us is a live movie. We want to know what's going on, right? There's a person with a hammer, and image captioning, right? If you have an image, can you caption it? Can you generate a story from that image so that we can understand what's going on, right? And a lot of that has to do with spatial representations, right? So we can see here, there's in the lower right-hand corner, there's a person that's on a bicycle. Then we can understand some spatial relation to understand the higher order person on a bike, right? So all of this became possible within the last 10 years because of convolutional neural networks, which has dropped the error rate from that 16% all the way down into about 5%. And basically, we're going to study through this semester how those basic primitives take place so that you can use them in your own work. Okay, so if you looked at that graph earlier, right, and we look at the ImageNet system, which is here in the second column. This is the supervision, which was later called AlexNet. Okay, this was what was done. Okay, so in the year 2010, when the first system came out, they got about 25% error rate on the task of 20 classes. Basically, we were still following this idea of building up primitives, right? So you can see here, you might have a simple machine learning algorithm. You do some type of pooling of several different decisions about edges and then put them together to form a detector for some type of composite object. And then after that, go up higher and higher, okay? So that was using this hierarchical structure, and that has just been improved over time. Okay, so when we get to the year 2012, this was a system that looked very much similar to the 2010 system, but it was just using slightly more simple but layered technology. Okay, by simple we mean using a neural network. We're going to go over that within the next couple of weeks. And by layering we mean deep, right? So there's several different layers of the neural networks being put together to compose that. Right? So the supervision system had about 6 levels of nesting. Okay, and then 2 years later, they got more sophisticated. Okay, we could get better performance that people found, and basically they said, okay, by putting more layers on it, I can generalize better. I can find other structures. All right, and by doing so, I could recognize better. So in 2014, the GoogleNet system and the VGG system, they both had about 20 layers, so 20 layers of neurons. And then in the year 2015, things got really crazy, and then the Microsoft research people introduced a paper with over 200 layers in it. So just by a magnitude more, they were able to get a better performance. So in some ways, it doesn't stop there. We don't know what levels, what amount of layering will peak at the vision capabilities. So, even though AlexNet came out in 2012 and drastically reduced the error rate, the technologies for this came from a long time ago, right? So we're going to look at convolutional neural networks, but why they succeeded actually is contextually interesting rather than algorithmically interesting, okay? Why is that? Because actually it goes many years back, even back to the 80s or even before that, people were thinking about computing with very simple things like a perceptron, basically just an element that could do some type of linear regression, right? Take some weights on different features, add them together, and then decide whether to output a number or not. Okay, and people had tried in many instances to create neural networks from these architectures. Okay, and there was a lot of promise in the second wave of AI that neural architectures could achieve all of the goals that we wanted. Okay, they were wrong, but not because of the algorithms, because of the context. Okay, so where this came back, those neural architectures were invented in the 80s. Where this came back was in the late 90s. Okay, so Yanlei Kun, you may recognize this name. He's the Facebook AI director. Okay, he had created a system for the U.S. Postal Service to recognize handwritten digits. Okay, it's this very famous data set that is envisioned called the MNIST digit data set. It's basically a set of handwritten images on envelopes that people have scanned and labeled, so that they can try to figure out, what a 6 looks like or a 9 looks like on an envelope when it's written by a person, okay, when it's not printed out. Okay, and he had a very good system that was able to do this by using very similar technologies to the original neural networks that were proposed in the 80s. Okay, and if you looked at this, basically the compute power at that time was about 10 to the 6, maybe 1 million transistors. And the amount of data that was in all the images that were here were quite a lot too. Okay, they were order of magnitude larger. Right, so you have so much data, even though this is grayscale data, amount of images, data in an image is actually enormous, right? Because if you think about 1,000 by 1,000, that's 1 million already. And then if you have, 256 gray levels, that's 256 million possible things that you can have, right? So there's a lot of data there. And basically, the computing processing power that we had at that time was not sufficient enough to build large neural architectures. Okay? So it wasn't that the people who created neural networks was wrong, it's just that we hadn't caught up computationally to be able to do something about it. So what happened? Well, a decade later, there were 3 very big changes, right? First of all, Moore's law, right? So instead of having 10 to the 6, now we have 10 to the 9 on the CPUs that we were using. And we had a lot more training data. Okay, like we said earlier, when you are trying to recognize objects, if you don't have enough data to generalize from it, you're going to have problems understanding invariance, right? So if I take a picture of a cat and expect you to recognize a cat, but the cat moves, all right, then I'm generating a new image every second, right? All of those images are of cats. If we don't have all of those pictures, we don't have enough training data for that. So it was very critical to have enough data in order to recognize. And that's why they built this ImageNet data set, right? So we had much more volume of data to feed our algorithms, which is one of the things you hear over and over again about deep learning, right? That you need to feed lots of data to these networks for them to learn anything reliably. You have a small data set, which happens a lot in natural language processing, then you could be in a lot of trouble. Okay, so cases where things did work well is when we had a lot of data. For example, the first successes were not actually in vision, they were in speech recognition. Because speech is a continuous waveform, right? You can sample it at many time points. Every couple of, in like 10 milliseconds, you get another digit. So you can use that to create lots of data and have successes there. The final thing is in GPUs, right? So because people like to play games a lot, right? People created graphics processing units to compute triangles at a very high rate to be able to show on the graphic screen. And it turned out that you could reuse that type of architecture for general purpose computation, right? So there's this acronym called GPGPU, which means general purpose GPU, okay? And that trend took off, and that's what we use in deep learning today. Everyone's talking about graphics processing unit, and you may be wondering in the back of your mind, what does that have to do with games? And the answer is nothing at all, okay? The only thing it has to do with games is that those graphics processing units compute many things in parallels. There's basically these little devices that can compute a small amount of computations, but there's so many of them that you can think of them as a crowd of workers doing very simple tasks. Okay, so we can harness that because actually, when you think about a lot of these systems, they're doing the same operations on many, many different items. Each of those items could be a pixel or a patch, right? So if you have 1 million image pixels in a 1,000 by 1,000 image, and you have 1 million tiny processors, then you can compute over all of those, right? Whereas in a CPU, where you have a single unit to do that, it actually has to cycle through all 1 million points to process that, okay? Okay, so there are lots of other exciting things that you can see that people are doing in vision, so to do scene understanding. So perhaps you take a picture of a 2D image and you want to generate a 3D shape recognition from that, to do action recognition that you see in the bottom left, and even to generalize it, as I said, to virtual reality, where you have an object. If you have scene understanding, then you might know that this floor is not something that objects can fall through. You can't go through the ceiling and you can't fly. So you can generate graphics reliably in that setting. Okay, so scene understanding gets quite complicated. This is actually given by the PhD student who was lecturing this lecture, Justin Johnson. This is his work to do look at the primitives of how very basic objects can have relationships to each other, right? So you can think of this as the second level, and then try to use these this big scene graph to compute what's going on in the image as a whole. Okay, so what did they do? Basically, the ultimate objective of vision is to do understanding of what the sensor can see, right? So for example, in this image, they actually took images and flashed them for half a second to a human. Okay, so just flash like this, right? That. Okay, and then I ask you, what did you see, right? So this image, when presented to a person, somebody said, oh, it looks like some kind of game or fight. There's like people looking like maybe men who are throwing something, or I don't know, it looks like it was outdoors or something like that. Okay, so if we can get a computer to do this task, that would be one of the goals that we have. Okay, and actually scene understanding is actually really, really difficult because it requires a lot of semantic understanding, right? Semantics being the gap between what we see as objects that we might be able to recognize to understanding what's going on, right? So they offered this as an example, right? What is this image about? There's so much going on in this image that's not very transparent to a computer, okay? First of all, you see that there are people, right? That's easy to recognize. Object understanding can do that, right? Okay, and you see that maybe you recognize that there's a person standing on the scale, okay? And you might be able to say, okay, a person on a scale is trying to weigh themselves, right? And you see somebody standing behind him, and he's got his foot on the scale. And for us, it's very obvious to know that, when you do that, you're not going to get an accurate weight prediction. How would a vision system know that? No way, right? But there's more than that in this image, right? We know this particular person who's stepping on the scale, right? At that time, he was the president of the US, right? And the president of the US is supposed to have respect for his office, okay? Maybe not the current one, right? But the whole point is like, that person is supposed to be respectable, and he's doing something which semantically we know is not acceptable, right? And what's more, you see there are other people in the background, they're smiling. Why are they smiling? Because you can tell they know something about this scene. They're in the joke, right? So all of us, when we see this image, after a couple seconds, we find it funny too. How would a computer understand that? That's really hard. There's a lot of semantics that are going on in this picture, and that is the ultimate goal of vision, right? Is to put all of these things together and say, Barack Obama is playing a joke on this gentleman, this stepping on scale, and his aides are, finding that quite funny too. Okay, so there's a lot of other things that can go on with computer vision, and that's the ultimate goal, is to be able to put, not just the visual aspects about recognizing objects, but to try to be able to reach the human level of performance about understanding real-world knowledge, pairing it with our prior knowledge of how the world works, and putting that together to enhance our lives. Okay, so yeah, I'm not going to talk about what they did, but basically there's this online textbook. I think maybe many of you have seen this. I hope so. Okay, let's see. So there's this deep learning book that was put out by MIT Press. It's by Yoshua Bengio. He was the one of the creators of the Facebook AI and one of the creators of AlexNet. And he's written this book. You can buy it, but it's free on the web. So they're using this book as a textbook. So you may find it very useful to actually refer to this. And it's actually got a really nice section on the basics. So if you find what we're going to cover in the next, I don't know, 40 minutes or so a little bit too difficult, then please go through a couple of these chapters on linear algebra, probability, and numeric computations, and machine learning bases. Do all of you have some background in machine learning? Anyone does not have background? It's okay to say, yeah, okay, 1, 2, 3, 4, 5. Okay, most people on this side. Okay, great. So it's all right. So the next part that we do is going to be more on starting with the math, okay? So please stop me if I'm going too fast, because I think I will be going a bit fast for that part. Questions up to now? Okay, so hopefully you realize that vision as an object recognition problem at the state of the art right now is pretty good. Okay, we can get pretty reliable object recognition that's invariant to, rotation, lighting, and those types of things. We're going to find out how that works. And as far as scene understanding and semantics, we still have that very large semantic gap. And this is true in many fields in AI. For example, in natural language processing, we can get sentences, but to understand why that person said this sentence and what pragmatics does that mean. Okay, like, oh yeah, you're so thin or whatever, and you can hear the sarcasm, but computers can't, right? So they're puzzled. Okay. So we'll get to, in the later part of this course, other things that people do, which is some topics that are involving, for example, when you use a neural network and train on some image, if you have it generate back some things, what will it generate? It will generate very interesting pictures, right? Because if you reverse vision, then you're basically doing computational graphics generation. So you can, Google has the system Deep Dream, right? So this is a picture from that that's been trained after a while. And there's also things like neural style, which is, I think you may have seen in the popular press, that computers now can be trained to emulate an artistic style and transfer it to a picture. So you have a picture of a classroom and you want it to look like Van Gogh, then you take the neural network that's been trained on Van Gogh and then say, okay, Van Goghize this picture, and then it comes out like that. So these are all the same picture that have been transformed in, I think this is Van Gogh, this has got to be, what's his name? The Scream guy, yeah. And this is Kandinsky, and this is Picasso or something like that. Okay, so different versions of that. Okay, so in Stanford they have 3 problem sets. We don't have that. They have a midterm. We don't have that. They have a final project. I encourage all of you in industry to actually do that. I think it's really worthwhile. Okay, and as I said at the beginning, at the end of this course during week 13, we're going to hold a poster session. Okay, so what I'd like to do is get all of you to present what you've done over the semester for your project, and it's just as a collegial way of showing each other what you've done. So basically what you'll need to do is find some data that you're interested in. It can come from your company. It can come from, like what they did is like take images from the web. Okay, it could be a data set that's already existing. So for example, there are some machine learning websites. There's some competition websites like Kaggle, or maybe it's called Kaggle, where you can download data sets and then try algorithms for just for fun. Okay. Okay. The course is mostly going to feature code snippets from Python. So if you have Python background, great. If you don't, then there's also a tutorial on their website to go through Python, and NumPy, which is a very important numerical library for making very quick work of matrix computations, okay, that you should learn. Okay, so that's all for this part. And I will go on to the next part. Shall we take a 5-minute break first? And then I'll start the second lecture. And then for those 3 of you, I think, who came in late, maybe you can introduce yourselves when we come back in 5 minutes, okay? All right, so I'm going to stop here, give myself a little bit of a speaking break, and we'll start after that.